In this part, we'll talk about how to learn a linear prediction model using SVM. And remember that in the linear prediction problem, or more specifically, linear classification problem, we want to separate positive examples from negative examples using a straight line. And basically, we're given some training examples. So these are all the pairs of x1, y1, all the way to xn, yn. And in each of these example I, it consists of an xi and yi. And xi is the input data. So it's a vector of d dimensions. And each of this entry is usually a real value. And we also have the yi, which is the class label. It's usually a binary label. And if it's +1, then it's positive. If it's -1, then it's negative. And since we are learning a linear model, so basically the linear model will be represented using W and also the V. So if we have the model, we'll just take the inner product between W and X. And then if this inner product is larger than some threshold, we will say that it's positive. And if it's smaller than some threshold, we'll predict that it's negative. So the problem is, which is the best linear separator? Of course, this linear separator will be defined by W and B. So basically, we're asking what is the best W and B. So should it be this linear separator, or should it be this one or this one? And usually we also call this linear separator the decision boundary or separating hyperplane. And before answering this question, let's first introduce the notion of margin. And we already know that the distance from the separating hyperplane or decision boundary actually corresponds to the confidence of the prediction. For example, let's say that we have these 3 points, A, B, and C. We can see that this point A is actually very far away from the decision boundary, meaning that the model is actually going to be very sure that this point A will be positive. And in contrast, this point C is actually very close to the decision boundary. Therefore, the model X is actually very unsure or uncertain that this point C will be positive. In fact, it might very well be the case that it's actually a negative point. And the margin here is basically defined based on the distance between points and the decision boundary. So basically the margin gamma is defined as the distance of the closest example from the decision boundary. So for example, let's say that we have a lot of training data points here, and this one is the decision boundary. And we can see that the margin is quite small here because the closest example to this decision boundary is actually very close to the boundary. And if you look at the other decision boundary here, we can see that since all these data samples, they are all very far from the decision boundary, therefore the margin gamma in this case is very large. And intuitively, you will think that the best decision boundary would be a decision boundary that can maximize the margin gamma here. And this is exactly the idea of SVM. And why do we want a model that has the largest margin gamma? This is because intuitively we want the decision boundary to have more room to make mistakes, right? And theoretically, we can actually also show that if we have a decision boundary or a classifier with the maximum margin, we can actually get a lower generalization error. So basically, this model will have better generalization ability. So the next question is, how do we compute or express the margin given all the data points and given the decision boundary expressed by W and B. Before doing that, let's remember something from the basic linear algebra. So basically, the dot product of two vectors A and B is it's equal to the length of A times the length of B times cosine theta, and the theta is the angle between these two vectors. So this is actually can be seen in this figure. And if you look at it more carefully, you can actually find that the product of the length of A and cosine theta is exactly the length of the vector A projected on the vector B. And interestingly, if you set this vector B to be a unit vector, then the length of B will be exactly 1. Therefore, the dot product of A and B will simply be the product of the length of A and cosine theta. So this term just go away. Now, let's say more concretely that we already have a decision boundary, which is W times X plus B. So this decision boundary is parameterized by the vector W and a scalar B. And this is in the two-dimensional space. So the W actually is a vector of 2 dimensions. And we also assume that this vector W has a unit length. So the L2 norm of this W is equal to 1. Now, let's say that we have one data point also in this two-dimensional space, XA1 and XA2. This is the 2 coordinates. And let's say that we have another arbitrary point, but this point is could be any point, but it has to be on the decision boundary. So we call this point XM. So these its 2 coordinates will be XM1 and XM2. Now the question is, how do we compute the distance between this point A and the decision boundary? So basically, we want to express the distance between A and this line L using WB and X1A, X1B. So this is basically our task here. And as you can see from the previous slides, if you want to compute the distance between A and this line, you can actually just compute the length of the inner product or dot product between the vector AM and the unit vector W here. We can see that this will be just the projection of this vector AM here onto this vector W. So this will be exactly the distance between A and this decision boundary. And we can expand this as the follow equation. So basically this will be just XA1 minus XM1. So this is the subtraction in the first coordinate, and this is the subtraction in the second coordinate. And notice that this point M is actually exactly on the decision boundary. And the decision boundary, we already know that the decision boundaries contains all the points that has the equation, the equality that W times X plus B equals to 0. So basically we have XM1 times W1 plus XM2 times W2 equals to minus B. Basically we can replace the XMW and XMW here with the constant B, which gives us this equation. And if we want to write it in a vector form, we will get something like this. So to conclude, we can compute or express the distance between any point A here and the decision boundary using just the dot product of A and W plus B, and we take the length of this vector. So this is actually quite a simple form. Now, remember that in the linear model, in a linear prediction model, we actually will just take after we learn the linear model, we will take the inner product of W and X, and we have we add B, and we'll take the sign to predict whether or not this data point X is positive or negative. And we already say that the confidence of a data point is actually the inner product of W and that data point, and we take the length. So basically, this would be equal to W times X plus B times Y. Why is this? This is because if W times X plus B is positive and this data also happens to be positive, then this whole number will be positive as well. And this is going to be exactly the distance between some data point X to the decision boundary. And if you happen to predict this incorrectly, then the confidence will just be negative. And this is also what we want. So specifically for the ith data point, we will have the distance of this data point to the decision boundary as gamma I, which is equal to W times Xi plus B times Yi. So this is coming directly from our previous slides. So the problem of learning a classifier that has the maximum margin is actually equivalent to solving this optimization problem. And you can see that this minimization here is just trying to find a gamma I that is the smallest. So that's basically trying to find a data point that is closest to the decision boundary, right? And we're trying to maximize this, meaning that we're trying to find a model represented by W and B that can maximize this margin. So basically, we can rewrite this optimization problem as this one. And we can see that this gamma is exactly the margin, because what it says is that we're trying to maximize a gamma such that for any point, for any data points, if we calculate its confidence or its distance to the decision boundary, it has to be larger than gamma. So this basically says that gamma is the margin, which is the distance between the closest data point and the separating hyperplane.